Hello everybody, I'm Sam from China. I'm so glad I can speak here and meet you all. Um, the title of my presentation is Hacking Windows CE. It focuses on the security problems of PDAs and mobile phones. Well, my presentation constructs with 8 parts. First of all, I will make a brief introduction for Windows CE. Because ARM processors are most useful CPUs in PDAs and mobile phones. So I'll talk about something about ARM processors architecture. Well, you know, memory management is very important for buffer overflow. So second, I'll introduce the memory management with graphers. As the name is developed by Microsoft. Because of the familiar APIs, so Windows developers can easily develop applications for Windows CE. Windows CE 5 is the latest version, but Windows CE.NET is the most useful version. And my presentation is based on Windows CE.NET. And for marketing reason, there are Windows mobile software for Pocket PC and smartphone on Microsoft's website. But they are also based on the core of the Windows CE. By default, Windows CE is in little endian mode and it supports several processors. But ARM processor is, almost all of the embedded operating system uses ARM as CPU. ARM processors are typical of RISC processor in that they implement load-store architecture. Only load and store instructions can access memory. Data processing instructions operate on REST only. There are 6 major versions of ARM architecture. The demonstrate device has a Samsung processor, which has an ARM9 core, and its architecture version is ARM v4T. More and more PDAs and mobile phones use Intel Xscale as a CPU, which architecture version is ARM v5TE. ARM processors support up to 7 processor modes, depending on the architecture version. These modes are user, FIQ, IRQ, supervisor, undefined, and the system. The system mode requires architecture v4 and above. All modes except user mode are referred to privileged mode. Applications usually execute in user mode, but on Pocket PC, all applications are running kernel mode. Well, I'll talk about it later. ARM processors have 37 registers. The registers are arranged in partially overlapping banks. There's a different register bank for each processor mode. The banked registers give rapid context switching for dealing with processor exception and privileged operation. In ARM architecture v3 and above, there are 30 general purpose registers. The program counter register, the current program status register, and file saved program status registers. 15 general purpose registers are visible at any one time. These registers are from R0 to R14. By convention, R13 is used as a stack point. In ARM assembly language and the C and the C++ compilers always use R13 as a stack point. In user mode and the system mode, R14 is used as a linker register, which stores the return address while a subroutine call is made. The program count is accessed as R15 PC register. You can access PC register directly using the data operating instructions. This feature is different from other processors, and it is useful for code location while writing shell code. Okay, let's move on to the next part. Understanding memory management is very important for buffer flow, but it's very different from other operating systems. Windows C, the memory management of Windows C is very different. So in this part, I'll introduce the details of it. Windows C uses ROM and RAM. The ROM stores the entire operating system as well as the applications that are bounded with the system. The ROM can maintain the files stored in it even without power of the battery. So the ROM in a Windows CE system is like a small read-only hard disk. The RAM in the Windows CE system is divided into two areas, program memory and object store. The object store can be considered something like a permanent virtual RAM disk. Unlike the RAM disks on the PC, the object store can maintain the files, maintain the data in the object store even when the system turned off. This is the reason that Windows C devices typically have a main battery and a backup battery. They provide the power for the object store to maintain the data. Another area of RAM is program memory. The program memory is just like the RAM in personal computer. It stores the stacks and heaps for the applications that are running. The program memory and the object store can be adjustable. The user can move the dividing line using the system control panel applet. Windows CE is a 32-bit operating system, so it supports 4 GB virtual address space. Let's look at this picture. And the up to GB is a kernel space. It's for the used for its own data, and the lower 2 GB is user space. From this address to below this address, memories are used for large memory allocation, used as memory mapped files such as object store. From 0 to below 420000. These memories are divided into 33 slots, each of which is 32 MB. Slot 1 is used as XIP, execute in place, which is a new feature of WinCE.NET. It expands the application's virtual address space from 32 MB to 64 MB. Slot 0 is very important. It's for the current active process. The first 64 KB is reserved by the OS, and the following is the processes code and data, and then followed by the thread stack and the process heap. DL files are loaded into the top address. Well, let's move on to the next part. WinCE treats process in a different way. WinCE it limits 32 processes being run at any one time. When the system starts, at least 4 processes are created. Let's look at this picture. First is the NKEXE, which provides the kernel service. It's always in slot 97. FileSys.exe, which provides file system service. It's always in slot 2. Device.exe, which loads and maintains the device drivers for system. It's in slot 3 normally. And GWES.exe, which provides GUI support. It's in slot 4 normally. The thread and WinCE just similar to the thread and other Windows system. And every process at least has a primary thread associated with it upon starting, even if it never created one thread. A process can create any number of additional threads. It's only limited by the available memory, and each thread belongs to a particular thread and shares the same memory space. But the set permissions API will give the current thread access any process. This API is used in such as debugger and some system function. And the ID of the thread and the process under WinCE is just the handle of the thread and process. It's very funny, and it's useful for a programmer. And each thread has an ID, a private stack, and a set of registers. When the process is loaded, the system will assign the next available slot to it. And then the DL files are loaded into the slot on the top address, and then followed by the stack and the default process heap. After this, then executed. When the process's thread is scheduled, the system will copy it from its slot to slot 0. It's not a real copy operation. It's just mapped into slot 0, and this is mapped back to the original slot that allocated to the process if the process becomes inactive. Processes allocate stack for each thread, and the default size is 64 KB, depending on the link parameter when the program is compiled. And the top 2 KB used to guard against the stack overflow. We can't destroy this memory, otherwise the system will freeze. And remain the available memory for use from the stack. The thread stack memory is reclaimed when it terminates. Okay, let's move on to the next part. API address search technology. This is very funny. And before exploit, we must have a shellcode to run on the Windows CE. Windows CE implements Win32 compatibility. The core DLL provides entry points supported by the Windows CE. So every process loaded the core DLL. The traditional method over other Windows system, Win32 system, is to locate the kernel 32, the base address of kernel 32, and then via PEB structure, and then search necessary API addresses via phead. So WinCE for the dust virus just use this method to implement its function. So we can just repeat it to our as our shellcode. Is there any structure like the PB structure? The answer is yes. The kernel structure, Kdata structure, will satisfy us. Kdata structure is defined in nkarm.h file, and it's a very important kernel structure, and it can access the foreign user mode by the fixed P user Kdata, and it keeps some important system structure such as module list and kernel heap and API set tables. The P user Kdata is defined in the SDK in the kfuncs.h, which fixed as FFFC800 on the ARM processor and file 5800 on other SPUs. Well, let's look at the last member of the Kdata structure. It's a A-in4. It's a D-word array. Well, indexed 9. Indexed 9. There is a point to the module list. So the A-in4 is offset 300 from the Kdata structure. So offset 324 from the FFC800 is the point to the module list. Well, let's look at the module structure. Module structure is defined in the kernel header file. The first is the point, is the self point just for the validation, and the second member is the point to the next module in the chain, and the third member is LPSZ mod name. It's point to the module names. It's a Unicode string. So we can locate the core DLL module by comparing the Unicode string of its name. Okay, offset 7C is the E32 member. It's a E32 lit structure. E32 lit structure is defined in the PHDR header file. We'll look into this instruction that E32 vbase will tell us the virtual base address of the module. So we can obtain the virtual base address of the core DLL. Okay, let's look at the E32 unit structure. This member is the info structure, and this structure is the first member is relative virtual relative address, and the second is the size. The info structure first is the export table position. So from now on, we also got the virtual relative address of export table position of the core DLL. Okay, I write a small program to list the virtual base address of the all loaded modules. This is the KData structure. It's FFFC800. And offset 724 is a point to the module list. And this loop will list all the loaded modules of the system. And offset 7C is the base address. Offset 8 is the DL name, and this is the Unicode string. Offset 4 is the point to the next module. But this address, the point of the module list is in kernel space, because most of Pocket PC ROMs were built with the full kernel mode option. So all applications appears to running kernel mode. So this loop won't get the access valid exception. But when we command of this instruction will switch our process to user mode. So when the system in the user mode, this loop will get access valid exception. In fact, the fopen will got access valid exception first. You'll understand while I finish the system call section. Well, I use this program to get the virtual base address of the core DLL is 1F60000. But when I use EVC debug to look into this memory, this data are invalid. The valid data is from 1F61000. I think maybe the Windows C is just for the purpose of save time and memory space. Then they doesn't load the head of the DL file, DL head. WinCE for the Dust virus use ordinals to find the API address, but I think comparing the API name to find the API address is more reliable for the shellcode, because the API name won't change even if the core DLL file is changed. To save size, we can also use the hash technology from the LSD's Win32 assembly components. So we can find the API addresses via the image export directory structure, like the other Win32 system. And this picture is ripped from SD's Win32 assembly components too, and it shows the way how to obtain the API address via the API name. Okay, the test ASM is our final shellcode. This shellcode constructs with 3 parts. The first, it call get export section to obtain the virtual base address over core DLL and its virtual relative address of export table position. Second, it calls find func functions to obtain the API addresses and stores it to the original position of the hash value. And the third is our implementation of our shellcode. It will modify a REST key of the Bluetooth, and then use kernel I/O control to soft restart the system. Well, most of the IPACs will open the Bluetooth while the device restarts. Microsoft provides several Bluetooth APIs, but HP company use Vidcon in the Vidcon Bluetooth stack for its PDAs. So the Microsoft's API have no effect on the IPAC PDAs. Well, there are some things to attention while writing shellcode. We must notice the LDR ARM assembly LDR pseudo instruction. This instruction will be this in the EVC debug, and the R4 rest depends on the program. So the R4 won't get the FFFC800 while the shellcode running, so the shellcode will fail. And this instruction will be in the EVC debug. It's okay when the shellcode run. And the Windows CE uses R0 to R3 as the first and the fourth parameters of the API. When if the parameters is more than 4, the other parameters are stored in the stack. So we must pay attention because our shellcode may be in the stack. We don't let the parameter destroy our shellcode. That's why my shellcode has these instructions. Just deal for the stack. Don't let the parameters destroy the shellcode. Otherwise, this shellcode won't succeed. EVC has several bugs that makes debug difficult and funny. EVC will change the stack contents when the stack reclaimed in the end of a function. It's really sucks because our shellcode may be on this stack, and this bug will destroy our shellcode, so we can't debug our shellcode while in the real environment. And the instruction of the breakpoint may be changed to the E6000010 in EVC. It's really funny. And EVC allows code modify the text segment without error while using breakpoint or your step-by-step to debug. Okay, this bug sometimes is useful. The ADA Pro 4.9 has a Windows CE debug. I tested its alpha version. It also has these bugs. So I think maybe this bug is Microsoft debug APIs. Well, the shellcode we talked about is very complicated and it can't used in the user mode. Is there any other method to implement shellcode? The answer is yes. Well, let's look at let's look at the Windows CE API implementation in the core DLL. This is the power off system API implemented in the core DLL. The system will check the kthread info field and test its if it is one or something. The kthread info is in two function, while the thread is created in here. if the application is in kernel mode, the K thread info is initialized by the MD created thread 2 function, while the thread is created in here. If the application is in kernel mode, the K thread info is set to 1. Otherwise, it will set to 0. So, if it's 1, the system will use the API set table to find the API implemented in the kernel space. Use the API set table. Otherwise, it will use this address. This is the system call of the Windows CE. Well, we talked that when we set the process to the user mode, the fopen will get access valid exception. That because it's in here. The API set table, the implementation of the API is in the kernel space. So in these instructions, we have got access valid exception. If the system in user mode, that the K thread info is 0, then the system will use system call, just like this. Some instructions, some API only use system call, such as case set. Such as set kernel mode API. It won't use the in kernel space. It just use the system call. Well, there is a formula to calculate the system call address. It's like this. It's very simple. Let's calculate the kernel I/O control API. I got the system call of kernel I/O control is like this. It's very simple. So this shellcode is very simple. It's just a soft restart the device, and it can execute in the both in the kernel mode and user mode. Okay, let's move on to the next part. In this part, I'll demonstrate a vulnerable program in the PDA. The Hello CDP is a vulnerable program. Well, it uses fread to read the bin file of the root directory to the buff variable. Buff variable only is defined here, just 512 bytes. If the bin file is larger than this size, the buff will overflow. And printf and the get char are just for test. Windows CE has no console. Um, uh, they have no effect, if the console DLL without in the Windows directory, and the console DLL, you can obtain the console DLL from the Windows Mobile Power Toy and Pocket Console. I prefer Pocket Console. Um, ARM assembly use BL2 call function is not like the such x64 886. Well, ARM use BL to call a function. And this store instruction is the first instruction of the hello function. It will store the LR rest to the stack. The LR rest contains the hello caller, the return address. It's just this address, and this instruction is the latest instruction of the hello function. It will store the stack. The return address of the which is stored in the stack to the PC rest. So after this instruction, the program will follow to here. So if we override the return address that is stored in the stack, we can obtain the control while the function, when the function returned. The variable's memory address allocated by the program is corresponding to the loaded slot, both stack and heap. So the process may be loaded into different slots and each start time. So the base address of its stack always alters. But we know that slot 0 is mapped from the current process slot, so its stack address is stable. So this is our exploit for the hello program. This is the stack address of the slot 0. It's pointed to our shell code. You can also use the jump address to our shell code. The first, I use this method to construct my attack buffer. The first is the padded buffer, and this is the return address. And the shell code is followed by this. Well, the PDA is frozen when the hello program is executed. It's really funny. I think maybe the stack of Windows CE is small, and the buffer overflow destroyed the 2 KB guard on the top at the stack address, the top of a stack boundary. So the device further. Well, I changed another method to construct my attack buffer. The first is the knob instruction, and then is my shell code, and the last is the return address. It will point to our shell code. This attack buffer is smaller than before. Well, this I use this the method is successful. The PDA restarts when the whole program is executed. I'll demonstrate it. Okay, this is my PDA, and the Bluetooth is closed. When I press any key, the system device restarts. Well, the system is okay. Well, the Bluetooth is opened. That means the system execute our shell code. Well, the Bluetooth is dangerous. I'll close it soon. Okay, let's move on to the next part. The shell code we talked about is just for test, and it will execute successful in my environment, but other program maybe filled the special characters before the stream buffer overflow, such as overflowed by str copy. The shell code will be cut by the zero. And it's difficult and inconvenient to write shell code without special characters. If you use R0 rest, the OP code maybe contains the zero. The newer ARM processors has Harvard architecture, which separates instruction cache and data cache. This feature will improve the performance of the processor, but it makes the self-modifying code is difficult to implement. And ARM 9 core has 5 pipelines, and ARM 10 core has 6 pipelines. The Intel X-Scale process has 7 pipelines. Well, I write a demo for the shell code decode. Well, this is the self-modifying code. This 4 instruction will modify the last 4 instruction. It will modify the 1 to 99. And between this instruction, I have so many pad instructions. This instruction is really funny. I execute. Well, the R1 to R4 all get the 99, but when you use execute in the Intel Xscale device, you must add two more pad lines. Then you can let the R1 to R4 all get the 99. That's because Intel Xscale has seven pipelines, and my environment is Samsung processor, which is R9 core. It only has 5 pipelines, and this instruction is the latest instruction of the hello function. It will store the return address of the which is stored in the stack to the PC register. So after this instruction, the program will follow to here. So if we overwrite the return address that is stored in the stack, we can obtain the control while the function when the function returned. The variable's memory address allocated by the program is corresponding to the loaded slot, both stack and heap. So the process may be loaded into different slots and each start time. So the base address of its stack always alters. But we know that slot 0 is mapped from the current process slot, so its stack address is stable. So this is our exploit for the hello program. This is the stack address of the slot 0. It's pointed to our shell code. You can also use the jump address to our shell code. The first, I use this method to construct my attack buffer. The first is the pad buffer, and this is the return address. And the shell code is followed by this. Well, the PDA is frozen when the hello program is executed. It's really funny. I think maybe the stack of Windows CE is small, and the buffer overflow destroyed the 2 KB guard on the top stack address, the top of a stack boundary, so the device frozen. Well, I changed another method to construct my attack buffer. The first is the knob instruction, and then is my shell code, and the last is the return address. It will point to our shell code. This attack buffer is smaller than before. Well, I use this the method is successful. The PDA restarts when the program is executed. I'll demonstrate it. Okay, this is my PDA, and the Bluetooth is closed. When I press any key, the system device restarted. Well, the system is okay. Well, the Bluetooth is opened. That means the system execute our shell code. Well, the Bluetooth is dangerous. I'll close it soon. Okay, let's move on to the next part. The shell code we talked about is just for test, and it will execute successful in my environment, but other program maybe filled the special characters before the stream path overflow, such as overflowed by str copy. The shell code will be cut by the 0. And it's difficult and inconvenient to write shell code without special characters. If you use R0 rest, the OP code maybe contains the 0. The newer ARM processors has Harvard architecture, which separates instruction cache and data cache. This feature will improve the performance of the processor, but it makes the self-modifying code is difficult to implement. And ARM9 core has 5 pipelines, and ARM10 core has 6 pipelines. The Intel X-Scale process has 7 pipelines. Well, I write a demo for the shell code decode. Well, this is the self-modifying code. This 4 instruction will modify the last 4 instruction. it will modify the 1 to 99. And between this instruction, I have so many pattern instructions. This instruction is really funny. I execute. Well, the R1 to R4 all get the 99, but when you use execute in the Intel Xscale device, you must add two more pattern lines. Then you can let the R1 to R4 all get the 99. That's because Intel Xscale has seven pipelines, and my environment is Samsung processor, which is R9 core. It only has 5 pipelines. Well, this method is just use store to modify the code, and I change another method. Well, this method. First, I use XOR to the last 4 instructions encoded with XOR with 88. And first has a loop to decode the last 4 instructions. It use load instruction to load encoded bytes, and then use EOR to decode it, and then stored the decoded bytes to the original position. Because this method use LDR load instruction, maybe it checks some other ARM cache architecture. So even if you fill a lot of pattern instructions, you won't get let the R1 to R4 get the 1. I'll demonstrate it. Well, the last 4 instructions were decoded correctly, but we can't get the correct value. So I failed in this method. Because the Pocket PC ROMs were built with a full kernel mode option, so the applications running kernel mode. So I can use the MCR instructions to control the the coprocessor and manage the cache system. But I use some method. I use some methods such as flush the iCache and drain the write buffer, but they have no effect. Well, the codes we talked about are the real-life buffer overflow example in the Windows CE. It's simple, but I think this technology will be improved in the future. The PDA has same thread. Because of the instruction cache, the decoding shellcode is not good.